Our next presenter will be Vincent Xiao from, I think that's how you pronounce it, from FTC VERTEX 15534, giving a presentation about odometry and FTC. I'll link their website in the stream. Anyway, take it away.
Okay, awesome. Can you hear me?
Yeah.
Yeah.
Okay, awesome. So I am Vincent. I'm on First Tech Challenge Team 15534 from Phillips Exeter Academy, and on the team I serve as the mechanical captain, which means I'm in charge of the designing and building of our robot. So today we will take a look at odometry, which is the real-time tracking of an object's position and heading, but more specifically the applications of odometry in First Tech Challenge. However, I realized that this stream, there are many people that are actually not on First Tech Challenge and from other FIRST competitions, other robotics competitions. So we are going to look at odometry through the eyes of an engineer, and more specifically, how to think like an engineer. So often the two words scientist and engineer are associated as the same thing, but they're actually quite different. A scientist works to understand a concept or discover new knowledge, while an engineer applies that knowledge to solve practical problems while optimizing cost, efficiency, and many other parameters based on the application. So while an engineer is more focused on the applied side of things and works to create and innovate and produce new ideas, an engineer also needs to be a scientist because they need to understand the concept in order to solve the problem they wish to solve. So one of the tools that engineers use very often is the engineering design process. This is used all over the industry in many robotics competitions as well. And I'm sure many of you have seen this before, but it's very important to go a bit more in depth into the engineering design process. It's obvious that the first step is to identify the problem we need to solve, but we also need to identify the constraints of the problem we wish to solve, because not everything is possible at all times. It's also very important that we research the problem and fully understand the problem before we jump into imagining possible solutions for a problem. So our first step is to identify the problem. And for those of you not familiar with First Tech Challenge, the game goes like this. There is a 30-second autonomous period and then a 2-minute driver control period. So what this means is for the first 30 seconds of the match, the robot has to do all the tasks by itself. So there can be no driver interactions. But in the following 2 minutes, the robot operates based on commands from 2 drivers and a team coach. So these 2 drivers work together on 2 gamepads to drive around the robot. So over here, we do have a score breakdown of the First Tech Challenge Skystone game that was this past season. So if we see, even though autonomous is the shortest period and has no driver interaction, arguably making it one of the most difficult periods, you can see that there are a lot of points over here available in the autonomous period. Whereas in the driver control period, there's not many points. Obviously, these tasks in the driver control period can be repeated over and over and over again in order to amass a large sum of points. We see that right away, autonomous has a lot of points. So here we have our first problem. Driver controlled is obviously much simpler because you have 2 people that can drive the robot, can fix things in case something goes wrong, and you even have a team coach that can advise the drivers on what to do. And so in driver control period, you have less points, but it's much simpler. Whereas in autonomous, it's much more difficult. The robot's doing everything by itself, and there's so many points available. So naturally, we want to try to gain as many of these points as we can. So the first logical step would be to make our robot very consistent and very precise. And we can do this by making our robot move slowly, adding acceleration, adding deceleration. And we can do all these to make our robot more consistent. By moving slower, we do not have the risk of breaking traction. By adding acceleration, our wheels will not slip. So we are always in a predictable situation. But then we have to take into account all of the factors when making a decision. And one of the factors is time. And autonomous period only lasts for 30 seconds. So it's very difficult to be precise at acceleration, make slower movements all in 30 seconds while accomplishing all the tasks we want to do. So then naturally, we will want to jump to another idea, which is to move faster. So to the right here, we have an example of a robot moving super fast. So as you can see, this robot is moving very, very fast, but it's not very controlled. It's not very precise. And yeah, look, the battery just fell out of the robot. So that's also what we don't want to do either. By making the robot go super fast, we're compromising the accuracy and the precision that we wanted earlier. So when we are brainstorming solutions to problems, we must make sure they're feasible. For example, we can't just say, make the robot go slow or make the robot very consistent because we have a time limitation. We can't just tell it to go fast because then we're compromising on the consistency that we established that was necessary. And we also must take into account many factors, including the trade-off between quality, time, and cost. So this is where odometry comes in. Odometry is the real-time tracking of a robot's position and heading or direction on the field. So it can represent the robot's position on the field as a set of coordinates, x, y, and a direction or an angle, which in this case we will say is theta. So odometry does this by using 3 dead wheels. They're circled in red over here. Here's our right odometry pod, our center odometry pod, and our left odometry pod. And what these do is when the wheels spin, we have a sensor that senses how far the wheel is spinning. And then we can use math in addition to these 3 encoder readings to convert these values into a measurement of x position, y position, and heading. So how does odometry solve the problem? So one of the main problems is not being able to go fast enough while still maintaining accuracy. And that is because first tech challenge robots are traction limited. And what traction limited means is that the motors allowed in first tech challenge are plenty strong, but the faster we go, the more our wheels will slip. And then so we break traction and we are no longer being very precise. So one of the main features of an odometry pod is this spring in this red box over here. And this spring keeps this odometry tracking wheel tensioned to the ground really tightly. So what this means is even though our drive wheels can spin, this wheel will never slip because it is always properly tensioned towards the ground. In this setup over here shown in this image, this wheel has roughly 2 pounds of tension being put on it against the ground. So this means that the wheel can't possibly spin, so it will always track the ground perfectly. And since our odometry pods never spin, our robot will always know our odometry pods never slip. Our robot will always know exactly where it is on the field because there is no inaccuracies introduced through this system. So odometry therefore allows us to go as fast as we want while maintaining accuracy. So here we have an example. Let's say on the left side here, our robot wants to follow this path on a dotted line. And this is during the autonomous period. So the robot's going along its path, but then our alliance partner, the robot makes a mistake and hits our robot. So now our robot is shoved to the left over here. Without odometry, our wheels slipped, so we were shoved to the left. But we have no knowledge of being shoved to the left. We still think we are right here, when in fact we have been pushed over here by a partner. So naturally, we will continue along our planned path and end at our destination, which, as you can see here, is not equal to our desired destination. Odometry, however, does not prevent our robot from slipping. So here, our partner still collides into us and our drive wheels still slip. And so our robot is still pushed to the left. But however, since our odometry wheels are always tensioned to the ground and they never slip, our robot knows that it has been pushed to the left. So therefore, instead of continuing along the path to the incorrect endpoint, we can incorporate other tools such as motion profiling with odometry so that we can use the knowledge of where we are to get back to where we want to be. Here's another example. So in this case, our robot is moving along this arc really fast because we want to get from one point to the other endpoint really fast, and an arc is a pretty optimal path. However, we know that an object traveling in a circle will tend to want to proceed along a tangent along the circle. So if we're going too fast and the wheels on a robot break traction, that's exactly what's going to happen. Our robot is going to move along a tangent on the circle, and now we are no longer on our desired path. Once again, without odometry, our wheels slip and we have no idea where we are, so we continue the path and end at the incorrect endpoint. With odometry, we still slip. Odometry cannot prevent us from slipping. Our drivetrain wheels still slip. But once again, our odometry wheels do not slip, so we are able to correct for our mistake and still end up at the endpoint. So by now it's apparent that it's useful for making autonomous more consistent, but it can actually help solve errors in autonomous too. So here we have a clip of our robot in late November. So it's going to retrieve a stone and it's going pretty well, but here it overshoots the turn. Even though it has overshot the turn here, we have odometry. So our odometry knows that we have turned too much. So our robot then automatically proceeds to correct that error. So odometry is really useful because we can not only make sure we stay on our path, we can not only make sure we can go fast and be consistent, we can also correct for mistakes. For example, if our wheels slip because there's some debris on the field, or if another robot collides into us, we can always fix that because we know where we are. So that's why odometry is very important. So now that we have our problem, we need to brainstorm solutions. So the first step is coming up with the hardware necessary for odometry. So the hardware mainly consists of odometry pods, and these are the actual units that house the wheels, that house the sensors that will tell us the encoder values, which we then convert to position. So down here we have three very different designs to odometry pods. Right away we can see that the wheels they use are different, the sensors they use are different, their mounting techniques are different. So this raises many questions. For example, what encoders do we use? What wheels do we choose? How can we make our odometry pods track accurately even over obstacles and terrain? And where on our robot do we place them for maximum accuracy? So once again, we need to take a look at the engineering design process. We have identified the problem and identified the constraints of our problem. And then so now we are on to the brainstorming solution. And we've got the solution of odometry. So now we are at selecting a design. So it's very important to look past the current stage we're on, and we see the next stage is build a model or prototype. And the word prototype is very important because most likely the first thing you build is not going to work. But it's very important to get that prototype out there so you can test your design before you test and evaluate and optimize the design until you reach your final solution, which then you can share. So the encoder is arguably one of the most important parts. Actually, it is one of the most important parts of an odometry pod because this is what directly measures how much the wheel is spinning. So in order to make our odometry system accurate, of course, we want our encoder to be accurate. So here we have two of the most common options used in First Tech Challenge. Here is the S4T encoder from US Digital, and here we have the Rev through-bore encoder from Rev Robotics. So each has pros and cons, but mainly the S4T from US Digital has a lot of configurable options, so you can get it very, very, very accurate. And it's very compact as well. Whereas the Rev through-bore encoder is much less accurate and it's much bulkier. These are not to scale, but the Rev through-bore encoder in real life is much bulkier than the S4T from US Digital. So at first, it may seem like the S4T from US Digital is of much better value and is a much better choice until we take a look at the other considerations. For example, the S4T is over twice the cost of a Rev through-bore encoder. For a standard odometry system, you need about 3 or 4 of these encoders. So if you go for the S4T system, you are looking at over $200 just for the encoders alone. You're not even looking at the wheels or the other supplies necessary. Just encoders will run you over $200. Whereas the Rev through-bore encoder, you can get 3 of them for less than $100. So the Rev through-bore encoder is clearly much cheaper. And since cost is a big factor in FTC, many teams have to seek sponsorships. They don't have enough funding. The S4T may be very expensive. It's also important to note that while the Rev through-bore encoder is much less accurate than the S4T from US Digital, the Rev through-bore encoder is more than accurate enough for most FTC applications. So it may be overkill to go for the S4T from US Digital. You might also be tempted by the small footprint of the S4T of the S4T over the Rev through-bore encoder. But then we also have to look at other factors in the S4T encoder, primarily the mounting system. If you see here, the gold part, those are actually threads. So this S4T encoder is mounted by screwing it on to something. Whereas on the rev through bar encoder, you have these nice mounting holes that you can directly bolt onto an assembly. So it might be a bit tougher to mount the S4T to your odometry enclosure. Moreover, the output shaft on the rev through bar encoder is a female hex, which is very commonly used in FTC. So this is also a very big benefit because it incorporates a shaft that is already widely used. Whereas the S4T from US Digital gives us a simple round shaft. So that's not ideal. The hex shaft will be much easier to work with, and it's already a standard in FTC. So now we have a bunch of pros and cons of each. So now we just have to compare the two and pick the one that is best for applications. So here we see the comparison between quality versus time and cost. So for example, if we are looking for a quick and cheap encoder, it may not be always the highest quality. So in this case, that would be the rev through bar encoder. It's much cheaper, it's much quicker, as in it has much easier mounting points, mounting options, it's quicker to utilize. The quality of the encoder is obviously much lower, it's much bulkier, the materials used are a bit worse, and it's less accurate and gives less accurate readings than the S4T. However, if your team's limited by funding, then the S4T may not be a good option because it's over twice the cost. Our team personally used the S4T encoder this year, and we see no reason to switch to the rev through bar encoder because we already have the S4T encoder and already using it, and it works very well. But for a starting team, a rev through bar encoder may be a better option because you can actually mount it via the bolt-on holes, and it has a common output shaft, and it's very budget friendly, interfaces directly with our FTC control system, and the readings are accurate enough. So now another very important part of an odometry pod are the wheels. And the wheels are very important because that's the contact point between the odometry pod and the ground. If we have a bad wheel and it doesn't make good contact, then our odometry readings can be less precise than desired. However, here we have two very good options. This one here, you see, has two layers of Omni rollers. So it has one layer of green rollers on this side and another layer of rollers on this side. Whereas this is called a single Omni wheel, meaning there's only a single layer of rollers. So on this double Omni wheel, this is beneficial because since there's rollers at every point of the wheel due to the double roller design, the wheel will be much rounder than this wheel, which has kind of have these notches where the rollers are not present. But obviously, due to the double Omni is much bulkier and much larger. But in this case, both Omnis are of comparable cost, they're of comparable quality, and they are of comparable usability. So in a case like this, when choosing between two wheels like this, where all factors are comparable, we need to look beyond the surface level factors and dive a bit deeper into what these wheels will actually be doing. So in the center here, we have a CAD model of an odometry pod. This one uses a double Omni wheel, but that doesn't really matter. And down here, we have 4 sketches of the same CAD model, but just rendered with simple rectangular shapes. We see that here, these dark gray, that's the double Omni wheel. Here we have a single Omni wheel. The pivot point in the CAD model is represented through the pivot point here. And then we have represented the contact point of the wheel with the ground by this gray and red circle. So if we first take a look over here at the double Omni side, we see that the odometry pod can pivot up and down, obviously due to the pivot point. And we need the pivot point so we can go over obstacles, or if the field is not perfectly flat, if there's a bump or something, we need to be able to go over that. So in this case, the pivot point is a bit higher. This could be due to a dip in the field, or this could just be the natural resting position. We see that the double Omni makes contact with the ground at this point of the Omni wheel, which is the outer edge of the Omni wheel. And then here, the pivot point is lower than over here. This can be due to a raised bump in the field surface or some terrain. If we look at this, we see that it actually contacts the ground at this corner, or the complete opposite corner than this corner here. So now if we measure the distance between the fixed pivot point, which is directly fixed to the robot, and the contact point, we can measure them and compare them over here. We see that the distance between the contact point and the pivot point actually varies very significantly depending on the terrain the robot is on. So this obviously is not desired because this means we will get inaccurate readings because essentially the position of the wheel changes as we go over terrain or as the field is bumpy. Now, if we take a look at the single omni wheel, we see that since the wheel is much, much thinner, when the odometry pod pivots up and down due to terrain, the contact point does still change from the inner corner to the outer corner, but the change is not that significant. As we compare the distances with these purple lines over here, we see that they're very comparable, and this is negligible for FTC purposes. So based off of this comparison, it may seem like single omni wheels are a much better choice, because as we can clearly see here, the double omni introduces many inconsistencies and essentially just shifts the position of the wheel around, which will very heavily affect our calculations. However, the single omni wheel also has some of its own cons. The double omni wheel is very round, meaning it's round all the way around because of its double roller design. As I talked about earlier, the single omni wheel, it kind of has these divots in here where the rollers are not there. So the rollers kind of protrude out from the wheel. And since we have about 2 pounds of downward force pressing this wheel down, the wheel will naturally want to rest in its lowest possible position. And since the rollers are raised out of the surface, the wheel will naturally want to rest in the position such that one of the divots is in contact with the ground. So this is the lowest possible position the wheel can rest in. So this also introduces a big problem. Let's say our wheel is resting such that one of the rollers is in direct contact with the ground. The force downward from the spring will tend to shift the omni wheel such that the omni wheel will rotate in a certain direction so that this divot is in contact with the ground. So that's also not good because let's say we're just moving forward, the center omni wheel here could drift in order to settle down in this more natural position. So this will also cause many inconsistencies because this wheel will just be turning for no random reason because it wants to settle in its most optimal position. So we basically have to weigh the benefits of the two. The double omni wheel is not perfect, as we saw here, and the single omni wheel is also not perfect, as we see here. Our team personally, we chose the double omni wheel because we feel the double omni wheel is a little bit more predictable. We can also change the geometry of our odometry pod. As you see here, the pivot point here is here, but the axle of the wheel is below the pivot point. And we can also adjust the distance between the pivot point and the wheel, the offset of the wheel, and we can just alter the geometry so that the distance here becomes less and less, so it becomes more accurate. However, with the single omni wheel, this is completely unpredictable. You never know when it's going to randomly turn, and these random rotations will definitely cause inconsistencies. So as a team, we prefer the double omni wheels. So here we have a display of 3 designs of odometry pods, and we see that they've all taken different approaches. Most noticeably, these 2 teams here have incorporated the double omni wheel, while this team over here has decided that a single omni wheel would be the better option. We also see that this team and this team utilize the S4T encoder from US Digital, whereas this team has decided to go for the Rev through-bore encoder. So while there are many differences, there are also many similarities. For example, they all have a spring springing them to the ground. Although these 2 teams use linear torsional springs to directly pull the wheel towards the ground, this team uses a unique spring on the pivot point to spring the wheel on the ground. But there are also other things in common. For example, they all utilize a fixed pivot point. These 2 odometry pods are fixed directly to the robot, while this pivot point is fixed to a connector piece, which then connects to the robot. So here we see the major components of an odometry pod. Of course, we have the encoder mount. We need an attachment point for the spring to spring the pod to the ground. We need a pivot point where the odometry pod can pivot up and down to go over obstacles and where it will attach to the robot. And obviously we need the wheel, axle, and all that hardware to mount the wheel. In this particular design, this design uses 2 gears. It uses gears to transmit values from the wheel to the encoder. This is because of the difficult mounting style of the S4T that I talked about earlier. The S4T output shaft is very short, it's very uncommon, and you have to screw it on in order to attach it. So it's very difficult to attach the S4T encoder to the wheel directly. So you had to go for a geared design in order to transmit rotational values from the wheel to the encoder. So once again, one of the most important things to do is to take into account all possible factors when designing a mechanism or a subassembly. So here we have a prototype of an odometry system. So here we have the left vertical wheel, the right vertical wheel, and then the center wheel. This should be enough. We can use this to measure strafing or moving side to side. We can use the left and right to measure forward and backwards movement, as well as turning. But however, if we take into account other factors such as the terrain, we realize that this design is suboptimal. So let's focus on this horizontal wheel here. First, we see that the pivot point of this wheel is actually oriented such that it runs alongside the robot, like from front to back. So what this means is if we look at the center wheel and our robot is going forward and we have this obstacle such as this, since the pivot point is pointing towards the direction of travel, when we approach this obstacle, this wheel is not going to be able to go over that obstacle. If we do that, what's going to happen is this enclosure is going to crack, the wheel is going to be damaged, the encoder could be damaged, the gears could strip, the pivot point could be ripped out of the robot, and that is not desirable. So even though this would work on flat terrain, we need to take into account all factors, including terrain, when making our design choices. So let's try a new design. So this time, instead of having the pivot point run front to back along the robot, we have this run from left to right along the robot. We still have the same setup with 2 vertical wheels and 1 horizontal wheel measuring the same exact thing. But since this time, the pivot point is not oriented towards the obstacle, the pivot point can actually pivot upwards when there's an obstacle, as you can see here. So we have an obstacle, the pivot point actually allows the wheel to roll right over. And that is very useful because by allowing our robot odometry wheels to roll over obstacles, this means we do not need to avoid them, we can go over them, and it just increases our speed overall. Of course, this will introduce inconsistencies by going over the obstacle. Going over the obstacle could shift the position of this wheel a bit, but it's better than damaging an odometry pod or not being able to go over an obstacle at all. So now we have a design. We've settled on a design that takes into account all the factors that we need to take into account. So it's time to make a prototype. Obviously, if you're limited to certain tools, then only use those tools. But if you're not and you're seeking a new tool, we must once again balance time, quality, and cost. Of course, you can produce an odometry pod using a $500,000 HASS CNC machine, but that's not suboptimal per se, but it will create very, very high quality product. It's probably never going to break. It's going to have perfect machining tolerances. It's very smooth. Everything's going to fit perfectly, and you'll probably never need one for your whole lifetime. However, it's extremely expensive and the machining time is very high. So for FTC purposes, we can look at a more economical option such as a 3D printer, which is the resource that most teams already have. For odometry, a 3D printed housing is more than enough and is very robust, especially if you use the appropriate filaments for the 3D printer. Moreover, most 3D printers can be purchased for under $500 these days, so it's not as big as an investment. Now that we have our odometry pods, it is important to place them correctly on the robot. So first we need to establish what we want the odometry pods to measure. So we have 2 vertical odometry pods here, one on the right side, this is the underside view, one on the right side, and then here we have one on the left side. So obviously, since these are facing the forwards direction of the robot, these will be measuring how far the robot moves forward and how far the robot moves backwards. Since we have 2 of them, we can also use them to measure how far the robot's turning in either direction. And then since we use the mechanism drivetrain with these wheels here that have 45-degree angled rollers, which allow us to go sideways, we also need a 3rd odometry wheel here. And this measures how far we move sideways. So since we know this, we obviously want this wheel to be mounted horizontally on the robot, and we want these wheels to be mounted vertically on the robot. So first, to mount the vertical wheels, let's take a look at two circles. We have this blue circle, a larger blue circle, and then this smaller green circle all around the central center point. So let's say we have 2 points on the circle that correspond to each other. So 1 point here on the green circle, 1 point here on the blue circle. If we have the point make the same revolution in the same amount of time, obviously the point on the blue circle will have to move much faster. So therefore, a point on the blue circle will move farther per degree than the point on the green circle will. So therefore, the point traveling on the blue circle will be of greater accuracy. So from this, we see that the larger the circle, the greater the accuracy will be. So naturally, we want to place our odometry pods such that they are as far apart from each other as possible to give us maximum accuracy. Now, looking at what we want the horizontal pod to measure, we want it to measure sideways movement or strafing. So naturally, we want it to be in the center of the robot, right here. What that would allow us to do is it wouldn't spin on turning and would be very precise. But sometimes that's not possible. In this year's game, we have this intake ramp wheel that assists with the loading of blocks. So that basically blocks off this whole center segment for a wheel, so a wheel could not be placed there. So putting it here is suboptimal, because what this does is when our robot turns, we're not strafing sideways. But because this wheel is not directly in the middle of the robot, this wheel will still turn. So that will introduce some inconsistencies. Of course, we can take care of those through some extensive math, but it would be much more optimal to have it in the center of the robot. So we've solved one problem. So we've solved the problem of what problem needs to be solved. We've solved the problem of how we're going to solve the problem. In this case, we use odometry. We've designed an odometry pod that takes into all factors, that takes into consideration even things such as cost, quality, and time. And then now we have made a prototype and we have mounted them on our robot. So now the question arises, how do we convert these 3 encoder readings into a measurement of position and heading? The short answer to this question is math. And there's a lot of math involved. And there's plenty of resources online. Odometry is used all over the industry, so I'm not going to go into deep detail about the math, but we are going to look at how the odometry system actually establishes position in a more theoretical view. Once again, the design process pops back up. So right now, we have identified the need, in this case, the need to convert our encoder values into a position or an XY coordinate and a theta heading. So now what we need to do is we need to research the problem. This researching the problem is a very, very important step, as I mentioned earlier, as it can give us insight into what we're working with, and maybe it will even tell us what we don't have, what we need, or it might even speed up the process of imagining possible solutions. So taking a look at researching the problem, we can first take a look at what do we get from the odometry pods that we spent so long designing and building. Well, we just get an encoder value, and the encoder value most often of the times just tells you how many times the wheel has spun. So for example, the encoder on the center wheel will tell us how many times the center wheel has spun over the last X seconds or whatever. We can easily measure the diameter of the wheel and convert that into a distance because we know the circumference of the wheel and therefore multiply by the rotations, and then we get the distance that the wheel has traveled. So overall, the information we get from the pods are how far has the left omni rolled, how far the right omni has rolled, and how far the center omni has rolled. So now, continuing to research into the problem, we have to take into account how our robot's going to move. And obviously that's with our drivetrain. And our drivetrain is powered more often than not by 4 motors. And that's going to propel our robot wherever it needs to go. And then by our robot moving, that's why we need our odometry. But we may notice that more often than not, a robot seems to be moving in a straight line, but it really is not moving in a straight line. Here in black, we have a motor power curve of rotational speed versus the torque, and then a rotational speed versus power, and this will just show us the motor power. even though it may look like our robot is moving in a straight line, if we zoom into a very, very, very small time interval, the motor power essentially becomes constant. And when a motor power essentially becomes constant, the robot is moving in an arc, not a straight line. So in order for a robot to move in a straight line, you have to take feedback from the surroundings to constantly correct itself. So even if a robot looks like it's moving in a straight line, more often than not, it's just moving in a series of small arcs. So for this example, we are going to have our robot move in an arc. So here we have an illustration, a drawing of the bottom of our robot, even though this is the top view, this is the bottom view. So this is our left omni wheel. It corresponds with this left omni wheel over here. Here is our right omni wheel. It corresponds with that right omni wheel here. We're going to ignore the center wheel for now because we do not need it for our first calculation. So from this diagram, we see that this is the original center of the robot. And this is the new center of the robot after it makes its first movement. And it looks obvious. The movement is just an arc. The robot arcs to the left like this because the motor power become constant in small time intervals, and this is a very small time interval. So from this, the information we get from the odometry pods are simply L, or the distance the left wheel has moved, and R, the distance the right wheel has moved. So here, V is the position vector that describes the change in position of the center of the robot. So the center starts here and then moves here. So V is the position vector that describes the positional change of the center of the robot. We measure the change in position of the whole robot by the change in position of the center of the robot. So we can say that the whole robot moves by the vector V. Of course, the robot also turns to the left slightly, but that's a very easy calculation. So to express the robot's change in position, we need to know the components of the vector. We know the vectors here, but we need the components. And knowing basic math, we can express the components of any vector through x and y components shown down here. So this vector V has an x component of change in x and a y component of change in y. So we can represent the position change vector as a coordinate, change in x, comma, change in y. Of course, this is all relative to the original starting position. And so now we have a way of establishing the robot's change in position. Now we have to find a way of establishing the robot's change in heading. This is probably the easiest part. You can use a gyro sensor or an inertial measurement unit, which both give you an angle reading of which way the robot's facing. So that's very easy. Or we can also just simply calculate it through the difference between the left and right omnis. We can clearly see here that the left omni has traveled less than the right omni. So we can take the difference between the distance traveled and divide it by a constant, and then we can determine the angle that the robot is now facing. So now our robot is located at change in x, comma, change in y with a heading of theta degrees, but this is all relative to our starting point. So if our starting point was a coordinate 0, 0, we would now be at change in x, change in y with a heading of theta. So we can't overlook anything, and we have the center omni for a reason. So here we have added the center omni wheel. The center omni wheel here corresponds to this, which is J, labeled J in the diagram. We still have the left omni and the right omni once again. This image over here is a top view, here is a bottom view, so they don't necessarily line up perfectly. So here, the robot still moves in an arc, the left omni wheel still moves L, the right omni wheel still moves R. And we're moving in an arc, and we have not strafed at all. So we would not expect the center omni wheel to do anything. We would expect the center omni wheel to just stay at 0 since we're not strafing. However, if we look at the diagram, since our robot is turning theta degrees, our center omni wheel actually rolls. It actually rolls the distance of B. Since it rolls the distance of B, it may elude us to think the robot has strafed, but it has not. So this is another example of needing to consider all factors and researching the problem thoroughly before first implementing it. If we did not consider that the center omni would roll during an arc, that would be a huge error and would cause a lot of inconsistencies. As you can see, the amount it rolls is actually very significant. Of course, we know the angle that it rolls for, and we know the distance between the center and the center odometry wheel, so we can easily calculate that distance and cancel that out, but it's still important to realize that this omni will roll some amount. So in this case, in this simple arc here, we do not even need the center omni. The left omni and the right omni are all we need to calculate the change in position and change in heading. In this case, the center omni does absolutely nothing. But even though it does absolutely nothing, we still have to remember it does absolutely nothing and not use it in our calculations. So in this diagram here, it's a bit more complicated. So we have our original robot position here. Here is the left omni wheel, here's the center omni wheel, here is the right omni wheel, and here's the robot center. Our robot still makes the initial arc from this position here to that center there. And that will render us with a left omni here, center omni here, and a right omni here. Once again, left omni travels L centimeters to this position, the right omni travels R centimeters to this position, and even though we do not strafe, the center omni travels B centimeters throughout this arc. So now we have motion in 2 axes. So we're going to add a second degree of motion here. So here we're going to, from our final position, we are going to strafe to the right. So we strafe from a center robot here to a robot centered here. So we're just basically strafing to the right. So now the left omni strafes from here to here, the right omni goes from here to here, and the center omni goes from here to here. So this is where the center omni really comes in handy, because now we can directly measure the distance we strafed with the center omni. So we see here that the strafe, we're not turning at all, we're just moving directly to the side, and so that's what the center omni is for. So we see here that the center omni has rolled a distance of G centimeters. So that is the distance we have strafed to the right. So we've made 2 movements now. We've made 1 arc to the left and 1 strafe to the right. So we first used this red vector here, or change in x comma change in y, and a directional value, theta, to establish our first movement from this center to this center over here. Then we made a second movement from this center here to that center over there. And then all we needed to represent that was our center omni wheel. So to find our total position vector, knowing our first initial 2 vectors, we can just add them together to obtain our total position vector. So in this case, the total position vector represented in yellow would be change in x plus change in x sub 2, comma, change in y plus change in y sub 2. So this process of adding together smaller vectors to get a total position vector is performed many, many times per second. And this continually updates the position of the robot. And every time we update the position, it is called a refresh. And naturally, the more refreshes we do, the smaller the time intervals get, so the more accurate readings we get. It's also important to note that even though this vector was created by the sum of these 2 smaller vectors, we could have taken any path to this final point. We could have strafed to the right first, then arced, and still resulted in the same final position vector. We could have arced a tiny bit, strafed, arced, and then strafed again, and we would still end up at this final point. This was just an example to show how we could combine 2 motions to determine 1 final position vector. So now we can put this process all together. So we start at this point, and this point is 0, 0, and then we get to here, and then this has a specific coordinate which is determined by the sum of these 2 values. And then we reset, and this becomes 0, 0, and we make our next set of moves and then track our next positional value. Over here, we have a visualization of odometry. This white line is the path that our robot moves along, and this blue line is the odometry approximation of our path. We see that it is fairly accurate, but we also see that it is in blocky lines and there are no smooth movements. This is because of exactly what we did here. Even though we made a very smooth arc and then a strafe, our total position vector was simply a line. So when we put together our path, we just get a bunch of lines. So if we do very few refreshes, we get a lot, not many lines. So we get something like this, and that's not very precise. Even though we end up roughly the same area, it's not very precise. If we add some refreshes, we get more lines. Putting more lines together, it becomes even more accurate. And then this season, our team had 14 refreshes per second, meaning we were updating our robot position 14 times every second. So this would be an approximation of what that would look like. It no longer looks as blocky as slow refresh rate because we have more lines, and all the lines can be approximated into curves. So we get a very accurate approximation of the movement of our robot. So here we have a sample of our autonomous program from last year. So in this autonomous mode, we combine tools such as odometry with motion profiling. Motion profiling is it allows us to take 2 points and generate an efficient path between the two. So that's what we're doing. We're using our knowledge from odometry of where we are to where we want to go, and we use motion profiling to determine where we are. Since we were able to utilize odometry, we were able to go faster than most teams and be more efficient because we were no longer worried about our wheels slipping or being impacted by other teams' robots. Here's a sample of our code from this year. It may look complex, but let's focus on this blue box. And if we look at this, it really is not very complex. What this is telling us to do is go to the coordinate 17.5, comma, -27 with a direction of -135 degrees. So that's all we're doing. And then in the next line of code, we're telling it to go from this point to a new point. In this case, 17.5, -32. And as we see here, we maintain the same heading. So all we have to do is enter the coordinates because our robot in our odometry system automatically calculates where we are. So if our robot knows we are currently at this position and we tell it to go to a new position, we use other tools such as motion profiling to get us to this position. And odometry can double check that we are at this position. And if not, motion profiling can generate a path back to this position in case our wheels slipped or something. So the takeaways are that it's very important to use the engineering design process and isolate the problem. And not just use the engineering design process, but actually use all the steps of the engineering design process. After we have isolated the problem, we have to take into account all factors that might affect our designs. We have to take into account the limitations of our designs. And moreover, we need to use our tools, skills, and strengths. For example, if a programmer on our team has a skill of knowing motion profiling, combining our skills of motion profiling with our tool of odometry will give us a very powerful tool in First Tech Challenge. So to isolate the problem was not needing to be consistent. It's very easy to be consistent by going very slowly. And the problem is not needing to go fast. We clearly saw that it's very easy to go fast as well. But the problem was needing to combine speed and consistency, and that's where odometry came in. Have to take all factors into account. For example, we have limited funding as a team. First has rules set in place. You can't use coffee beans on your robot, for example. And moreover, we have to find a compromise between cost, quality, and time. So here we have a very common triangle between cost, time, and quality. For example, if you want something cheap and fast, it will likely be low quality. If you want something to be really fast and really good quality, it will be expensive. So and if you want something that's cheap and high quality, then it would be slow and low priority to accomplish. So there's no right way to go, but it's always a trade-off between these three. You can't have something be fast, high quality, and cheap. Another thing is we have to, once again, take all factors into account. We need to recognize this. Sometimes overlooking the simplest of things will result in needing a lot more time and energy and effort to fix. For example, this design looked pretty solid. It had a horizontal wheel, it had 2 vertical wheels, but it could not go over obstacles. If we overlook this one design flaw, and we were at a competition and we ran over pieces of debris, our center odometry pod could be ruined for the entire competition, and we may not advance to Worlds, for example. And that would be much more frustrating than having to spend a few extra hours designing a new middle odometry pod. And we have to use our tools, skills, and strengths. Obviously, most teams use a 3D printer to produce an odometry pod. Well, if you have a $500,000 HAS CNC, you're very welcome to use that. You will using your tools, you will be able to produce a much better odometry pod than everyone else. But if you only have tools such as a laser cutter, you can use that to prototype as well. You can combine laser cut PETG with standoffs to create an odometry pod, for example. We also can combine skills and strengths together. For example, odometry and motion profiling becomes very powerful in First Tech Challenge. So thank you for attending this presentation, and feel free to email me at vertex15534@gmail.com if you have any further questions, and I hope you were able to take something away from this presentation.
So usually we have a Q&A portion. Are you able to like answer a few questions? We have some questions.
Yes, of course.
Okay, so I don't know. So our first question from the chat is Cam. He wants to know what you're hoping to study after graduating. We can skip that one if you don't want to answer.
Well, I mean, definitely something along the lines of engineering. I'm not sure what exactly yet, but probably something related to STEM and engineering. But
okay, cool. And some other questions that we've gotten through that I've come up and a few other organizers have had. So in FRC, Kaylee and I are in an FRC team. We have like the WPI lab, which actually provides a lot of built-in methods to get teams started with odometry. Does FTC have anything like that? And if not, like what other tools do you use to build your own odometry systems?
right, so odometry has been relatively new. I think it was introduced in the past few years, and at the start there were like 0 resources for teams. But now there are actually many resources. Some teams, such as wizards.exe, forget their team number, they have a whole YouTube series on odometry, how to do odometry. For example, we provide our odometry code for the public. Many teams share their odometry designs. I don't think there's a specific place where everything's concentrated, but a quick search on YouTube, FTC odometry, will result in a lot of tutorials. I know wizards.exe provides their code, provides their CAD files, provides a build list, and has extensive series teaching you how to get started. But odometry there really isn't a correct way of doing odometry. So something like the wizards.exe tutorial would be a great way to get started. And then as a team, as you learn what works, what doesn't, you continue to develop your own system until you get it to a point where you like it.
So it's kind of like the first community itself is forming a basis for odometry. That's really cool. We have a question from Sarah Heimlich. How did you first get interested in odometry?
Oh, so yeah, so we attended the World Championships in 2019, and in one of our qualification matches, everything was going really well until an opposing alliance partner unintentionally dropped one of the game pieces into the field, and then our robot ran over that game piece, and then that caused our robot to be sidetracked. Then our robot proceeded to collide with one of the obstacles because our robot did not know it was being sidetracked. So after that, we really knew that we wanted to have a way to know if we were being sidetracked, if someone has collided into us. And we were also tired of having to test everything over and over again and use a time-based autonomous, because that's just very slow. So with odometry, we saw many teams at Worlds using that. So we decided to implement that so we could move faster, make autonomous more efficient and more consistent.
Great. We have another question from Jonathan Jesse. Testing our odometry has always been tricky. Can you speak to the diagnostic tools and testing strategies that you use to debug, tune, and verify accuracy of this odometry system?
Right, so there are a lot of, so odometry is just one part of the, like what I just talked about was just one part of odometry. Just knowing where you are on the field really isn't that helpful, because you also need tools such as motion profiling and pathfinding to be able to actually go anywhere with odometry. So there are many open source libraries such as Roadrunner that have been developed by Acme Robotics, and that allows you to basically enter in your odometry pod specifications, their location on your robot, and they will they have many diagnostic tools for that. But one of the tests that our team likes to do when introducing a new odometry system is we mark our robot on the field somehow to make sure that it's in an exact position. And then we have someone just push the robot all around the field in all different directions, spin it around, and then bring it back to the initial starting point. And then we can then check where the robot thinks it is. And more often than not, the robot will think it's somewhere like within 1 or 2 inches of the starting point. And then we know that our odometry system is fairly accurate and we just need to do minor adjustments in the code.
Okay. cool. There are a lot of questions about the software that you use. So what programming language do you use mainly to develop your odometry?
I'm personally not a programmer, but we use Java through Android Studio, like many other teams. Yeah, that's basically what we use.
Okay, cool. I'm just looking for a question. Is the odometry pod designed by your team, or did you like take other elements from other things you've seen? Just describe like how you came up with the idea.
Right, so we are actually from a boarding school, Phillips Exeter Academy, and we are very time limited. Though we do have the resources, we work in a space called the design lab, and that's only open for 5 hours a week. So that means we don't have much time to work on these things. So building a robot in itself is very tough. So at the start of the season, we were unsure of whether or not we would be capable of using an odometry system. So initially, we took the CAD files that were made public by Team 11115 Gluten Free, and then so we implemented those on a robot over the summer. So using that, we were able to test out the system and find out what worked and what didn't. And then so when the season actually started, we made minor modifications so that the pods would fit. We also added improved geometry to the pods so that they would track better over the obstacles we needed them to do. So we just basically took inspiration from someone else's odometry pod at first, and then we're slowly developing it into something that works better with our team and our design philosophies.
Okay, cool. That's really great. Have you ever explored combining odometry with machine learning to improve your complete solution?
We tried that for a brief period of time this year. So we were in January. For those of you that aren't familiar, this year's FTC game is basically giant Legos. You take Legos, stack them on top of each other to make a really tall tower. So when we were practicing driving, we realized that it was somewhat difficult in order to get the block we currently were holding aligned with the existing tower to stack it on. So for a period of time, we attached an external camera facing the back of our robot, and we were using that to track where the tower, the existing tower was. And then we attempted to use machine learning so that we could use odometry and the camera to guide our robot to the perfect stacking position. However, we were slowly running out of time. State championship was approaching, so we didn't really get that all figured out, but we did certainly try it, and I'm sure that if you would be able to get that to succeed, that would be a very powerful tool.
Okay. So this is a question that I have. With this odometry pod, you clearly used like a mechanism drive system in your robot. Would this work with other drivetrains, do you think, or is it unique to mechanism?
Well, absolutely. It would work for anything. It's just tracking the robot's position. So any robot that moves, you can use odometry to track its position. Of course, if you have something like a 6-wheel drive that is very, very hard to move sideways, then there might not be a need to use the center odometry wheel. That might be nice. Even for a robot that's very basic, like a 2-wheel drive or a tank drive, having the odometry will still allow you to know if you're being shoved around or anything. So I think it's very useful on all types of drivetrains, that we have stuck with mechanism because we just like the characteristics of the drivetrain.
Okay, thank you. Okay, what other questions do I have? What other sensors did you consider to know the robot's position?
The sensors, we only used odometry actually. The only sensors on our robot were the 3 encoders for the odometry pods. We had no other sensors except for like the built-in encoders to some servos or some other motors for other features. But the year before, we were using like an array of 6 distance sensors to try to measure, to try to make autonomous more consistent. But I think that with a good, finely tuned autonomous odometry system, there really aren't any sensors that would be necessary, although some sensors may be helpful, like a color sensor, a distance sensor can make some processes a bit faster and more consistent, but overall an odometry system should be fine.
Okay, and just one more question. This will be the last question. So are there any like sensors? This is kind of the second part of the question that you were just asked. Are there any like sensors that you'd want to experiment with next year?
I personally, for me, I don't think we need to experiment with any other sensors. This year we were using the integrated camera that was integrated with the phone. So the only sensor per se that we might venture into using is an external webcam for additional mounting capabilities. But we think that the vision from the camera and the knowledge of where we are on the field is enough. Of course, there may be new things that arise that maybe we would need to do something that a color sensor would be a bit more optimal for. But at least for the past 2 years, I think we would just stick with the odometry setup that we have, and we probably would not incorporate any other sensors to the drivetrain.
That's so great. So that is all the questions we have time for. Thank you for being here. Yeah, thank you, Vincent. Again, if you want to, I put the link to his team's website in the chat. FTC VERTEX. Go support them. Thank you.
Thank you.
Okay.